Okay, as I was saying, I will post recordings of these lectures. I'll crop everyone else's faces out. In fact, I should spotlight myself. Okay, well, okay, we'll see. We'll see what happens. But anything I post publicly, I'll crop everyone else's faces and voices out, which there's a chance your voice will not be cropped out of this first meeting. I don't know if I can figure if that setting is persistent, but otherwise your voice will be, in the future at least, your voice will be cropped out of anything I post online. So the online, like the videos I post online will just be the lecture with the screen share, and in fact, no one's face will be in it, not even mine. But I'll post them, I'll try and post them try to post them the same day I post the lecture, that the lecture happens. Every week there will be a handout, which is also where you'll find the homework, and homework is due weekly. So there's a week 1 handout that has the homework problems on it posted on the website, and you can go look at it. It says there's some idea of what we're going to cover this week, and also has the homework problems on it. And then depending on when you last looked at Canvas, when you joined, you might not have seen that I posted office hours. Office hours will be Thursday evenings from 8:30 to 10 p.m. I apologize that it's slightly an awkward time. For me, it's late. Maybe you're all younger, so maybe it's not so late for you. But anyway, so I have a young child and sort of no childcare, so there are sort of restrictions on my availability during the day, and so this was sort of the only time I have left in my schedule. But you can also, if you can't make it to office hours, you can always feel free to send me an email, and I'll try and respond as quickly as possible to sort of answer any questions about the class or homework. Okay, well, maybe I should ask, if people look through the syllabus, are there any questions about it? Okay, great. Well, feel free to, and if you think of a question, sort of or if you haven't read it and you looked at it and then later you have a question, feel free to send me an email. Okay, so maybe we can do a quick round of introductions. So maybe you can just tell us sort of what your name is, what your class status is, like if you're a first year or if you're an undergraduate or what have you, and where you are calling from, sort of geographic. I don't need to know like sort of the bathroom in sort of your parents' house, and but like geographically, sort of where you're calling from, whether you're in Utah or whatever. I'm Sean. I am in Salt Lake City, sort of holed up in my house, and I've been talking a lot, so I'm just going to sort of go. I'll ask you to introduce yourself, and I'll just go sort of around these screens as I see them, which is probably not as you see them. So Rebecca, could you introduce yourself? Thanks, Rebecca. And I should say, if I ask you to introduce yourself and you don't have a mic or you can't turn on your camera or anything, you can just ignore me and I'll move on. Antonia? That's fair. What time is it in Cyprus? Okay. Well, thanks for joining. Thomas? Thanks, Thomas. Boyana? Thanks. Jason? Okay, cool. Thanks, Jason. Sandra? Well, thanks, Sandra. and James. Cool. All right, thanks, James. Great. So I should say, and a couple of you had your cameras off, and that's completely fine. And at any point, you can have your camera or microphone on or off. So it's up to you, whatever you prefer. So, and there's one last thing I want to add about this. Well, actually, okay. So maybe I can just start talking about. I was going to say something about the course calendar, but maybe let me just say a little bit about the course, and I can say sort of something about the course calendar on the way. So this is 6320. So it's Modern Algebra 2. So I think you're all in the right place. So we recently reorganized the syllabus of the graduate algebra sequence. So it's a little bit, and it's now sort of a little bit unusual, I think, compared to most graduate algebra syllabi in the fact that we do like all of the ring theory and module theory the first semester, and then we do group theory sort of and related concepts like Galois theory and representation theory in the second semester. So I mean, somehow this is like very different than an undergraduate class, like your first class in abstract algebra. You would typically sort of learn group theory first, sort of start by sort of the basics of group, and then sort of you move on to like, then groups are sort of the algebraic structure with the sort of least structure that you sort of study regularly. And so then you sort of add on structure and you sort of study rings and things later on. And one thing I want to point out is we will take advantage of this. So I'm going to assume that you have sort of a strong and recent knowledge of rings and not always, but from time to time in the class. So we'll sort of use the fact that you have already studied rings in this class to sort of speed up some things. But the main objects of study really are sort of groups, then Galois theory, and representation theory. So I'll say a little bit more to introduce these ideas in a second, but let me just give you a rough idea of what our schedule is going to look like. And this is subject to change, but at least we can hope this will be true. It's the rough schedule. Let's see, so first week, which is where we are now. We're just going to do some motivation and then in some first concepts. So today we're going to sort of overview some things and talk about lots of examples of groups. And then on Thursday, the plan is to go over just some basic internal constructions of groups. So taking products of groups, taking free groups, free products. So there's sort of internal categorical constructions you can do with groups. There's sort of constructions where you take one group and you build new groups sort of from nothing except that group itself. So it's just like sort of when you study vector spaces and modules, you like do direct sums of modules and sort of products of modules and things like that. We're going to sort of study these same ideas for groups, like quotient groups and things like that, but we'll sort of put an emphasis on sort of a more sophisticated perspective on what's going on there. So actually let me ask in that vein, when you, like, for example, when you guys were doing tensor products of modules last semester, did you sort of did you talk about universal properties? Like, so do you say like what the universal property? Okay, I see some nods. Okay, good. Oh, and well, now I realize that my question was flawed. Could you just sort of raise your hand or do the thumbs up emoji if you were in last semester's algebra class? Okay, so Jason and Antonia, you were not, is that right? Okay, cool. Okay, thanks. So at least that question was sort of valid for most of you, and so you can fill in whatever your prior experience was if this was not a valid question. So it sounds like you did sort of talk about the universal property of a tensor product. Anyway, when we introduce sort of the main concepts of groups, we're going to sort of focus on their universal properties and sort of understanding how that is a way of defining what they are. But anyway, that's sort of Thursday, so ignore that for now. So weeks 2 to 5, this is really going to be about the structure of finite groups. So somehow, oftentimes in an undergraduate course on abstract algebra, the word group is synonymous with finite group. Like you think about like dihedral groups or symmetric groups or sort of dihedral groups or symmetric groups. It's been a while, so I'll remember some more groups as we move on. But you sort of think about these finite groups and you really are studying the structure of finite groups. And that's, so you prove interesting theorems, like for example, like counting theorems, like sort of counting the number of subgroups of some certain type, or orbit stabilizer theorem, which is about like relating the size, the cardinality of two things, which are just two numbers. So I mean, these are really, you use this finiteness everywhere in the theory. And of course, there are many groups that aren't finite that are interesting to mathematicians. For example, like GLN of R, so like n by n real invertible matrices form a group. And this is an interesting group that sort of people in math spend lots of time studying various aspects of. And so somehow group theory is much broader than just the study of finite groups. But somehow you can't say so much about like classification of groups in general. And there's not sort of some broad classification theorem for all groups. Whereas like finite groups, well, for example, if I like fix a number, like if I say how many groups of order 5 are there, that's like something you can answer. So some of you probably know the answer. Can anyone give me the answer? How many groups of order 5 are there? Yes, it's one group of order 5. Great. So Z mod 5Z is the only group of order 5. And this is something we'll talk about later on. But even if you didn't know the answer, like you could have done it by hand. Like you could have sort of written down like all possible, like, and you could have 5 elements and then you can sort of write down all possible ways you could sort of like define a multiplication on those elements. So anyway, you could take a pair of 2 of them and produce another one, and you could sort of check which one of those satisfy the axioms of a group, like have an inverse associative law, or satisfy the associative law, etc. So in like, you really can, somehow you can conceive that maybe you can actually sort of classify all finite groups, because sort of, at least like if you fix a number, like you fix an n, there are only finitely many of that n. And in fact, like in some sense you can. And so this is one of the great accomplishments of 20th century mathematics, according to some people. I don't know, it was definitely a lot of work people put into it. It's not completely clear how useful it actually is, but it was sort of a complete classification in some sense of finite groups. So there's a complete classification in the sense that sort of it classified all of the building blocks you can use. And then there's sort of the study of like how you can put together those building blocks. So the building blocks are called simple groups, and then there's sort of ways you can do extensions of simple groups to make new groups. And well, and this is thousands and thousands of pages, so obviously we're not going to prove the classification of simple groups in this class. But sort of this is sort of something that governs and sort of informs our approach to finite groups, this idea that you can sort of classify all of them. And so sort of when we talk about the structure of finite groups, like we're going to be talking about results. Oftentimes whose like main utility is that it allows you to sort of classify groups, like allows you to sort of pin down what they are. Okay, and so that will be weeks 2 to 5, and a lot of it should be familiar from your undergraduate course, at least maybe not at the same level, but some of the ideas should be familiar. So for example, probably a lot of you, if not all of you, sort of saw the Sylow theorems in your undergraduate mathematics. Maybe like, and it's often sort of like the last theorem in an undergraduate class on group theory. Okay, so that will be weeks 2 to 5 will be sort of the structure of finite groups. So week 6, we're going to do sort of an isolated topic in one hand, but on the other hand, it sort of will build into both Galois theory and representation theory. So we're going to talk about the character theory of abelian groups. So abelian groups are just the groups where multiplication is commutative. And so for a character of an abelian group just means a homomorphism from that group to the units in the complex numbers. So the characters is just a map from G to the complex numbers. So, and because it's sort of a finite group, like that's actually going to sort of land in a root of unity. So this ends up being, sorry, if G is a finite group, sort of that will end up landing in unity. We'll also need this for groups that are not finite. So other abelian groups. And so this idea of studying characters of groups is just sort of an intrinsically important idea. Like you can study sort of, somehow it turns out you can understand all abelian groups in some sense, many abelian groups, all in terms of this sort of very simple abelian group, the sort of complex numbers under multiplication, sort of, which is really maybe not that simple of an abelian group, but is like simple in the sense that sort of it's a very concrete thing in our head. And so you can sort of take a different abelian group and you can try to understand it by understanding how it maps to this group. So that idea sort of will build into representation theory later on. So representation theory is sort of taking groups and understanding the group by understanding how it can sort of act on a vector space by sort of linear symmetries. So that's sort of what representation theory is. And so this is sort of how a group can act on a one-dimensional space. So sort of C star is just sort of GL1. So it's sort of, these are the symmetries, C star is the symmetries of a one-dimensional complex vector space. So you're looking at sort of how a group can act on a one-dimensional complex vector space. This is one way to think about this. But this is also, and this plays a role sort of all over mathematics. Like, and if you've studied Fourier analysis before, if you studied the Fourier transform, or like the Fourier decomposition for like a function in a circle, then this is just this is an application of sort of the character theory of abelian groups. So in particular, sort of in this week, we'll talk about sort of doing Fourier analysis on finite abelian groups, and then we'll sort of end up proving a result that we need later on when we do Galois theory. So weeks 9 through 12 will be on Galois theory. I left a gap here, so I'll say more about Galois theory in a second, but let me say what's happening in week 7 and 8. So week 7, well, you're going to have review and a midterm. So the Thursday is your midterm, and the Tuesday will be just a review session. And then week 8, you'll have we'll have a break. So there's no spring break this semester, but we will have a spring pause. So during spring pause, class will be optional. There's not going to be any homework due in week 8. So there'll be a homework due on the Tuesday of week 7, but there won't be a homework assigned week 7 because you'll have your midterms. There will be no homework due week 8, and there will also be no homework due on the Tuesday of week 9. So sort of you'll really have a break, hopefully. You'll have a pause, hopefully. During that week, I'll do one meeting in the class where I'll just go over the midterm, and that'll be optional. You can come or not, and I'll just go over the solutions to the midterm. And then I'll do one day of class where probably people can just come and ask questions if they want. So it'll just be like an extra office hours session. Okay, so that's week 8. And then, okay, now we're back to the math. So Galois theory. And what is Galois theory? Well, let's see, what did I say above? So, and when I listed the topics of this class, I probably should have added field extensions. So a field is just a commutative ring where every non-zero element is invertible, like the rational numbers or the complex numbers, the real numbers. Sort of, I mean, on the one hand, like, so and algebra is sort of split into these two perspectives where, like, on the one hand, groups are the simplest things. because groups have like the least amount of structures you're prescribing. But on the other hand, like that's sort of only true if you're a robot. If you're like a regular person who learned mathematics, then fields are the simplest thing, because like fields are what we're working with sort of from day one. Like we sort of start working like, okay, you sort of briefly, you have a brief interlude in your life where you like integers are more sort of normal, but like pretty soon you start doing like sort of solving quadratic equations and things. And like, you're really like, you're working the real numbers, you're working the complex numbers, maybe you're working with the rational numbers. But in like in high school mathematics, for example, like all of high school mathematics basically takes place over the real numbers. And well, okay, maybe very possible that some of you got further in high school mathematics than I did. When my high school mathematics sort of all took place over the real numbers. So like somehow the structure that's actually in our blood and that sort of courses through all of our understanding of mathematics, sort of because it was sort of baked into us before we knew better, is the structure of a field. So like in that sense, like fields are actually the simplest things we study, because it's sort of the most familiar. Okay, and so in field extensions are just sort of about the ways you can put one field in another field. In particular, like Galois theory is sort of the study of a special type of field extension called an algebraic extension. And so, for example, the complex numbers are an algebraic extension of the real numbers, because you get them by sort of just adding a root of, by adding a square root of -1. So sort of square roots are sort of an algebraic operation. So you get it sort of by an algebraic operation. In general, sort of algebraic extension is one you can get sort of just by adding roots to some number of equations. And so, I mean, this is somehow an intrinsically, and I guess if you're a mathematician, you probably think this is intrinsically interesting, because like, if you're a mathematician, you probably think like solving equations is interesting, and like knowing when you can solve equations is interesting, and knowing sort of how you can solve equations is interesting. I guess it's not guaranteed, but a lot of mathematicians think those ideas are interesting. And field theory sort of gives this language of field theory and language of field extensions. It gives you a way to organize these questions about like when and how you can solve algebraic equations. And sort of the remarkable thing that sort of lies at the heart of Galois theory is that sort of this topic that sort of a priori could be of sort of unbounded complexity, like in some sense is sort of always governed by a very simple structure. So it's always governed by sort of some group structure. Well, that's Galois theory. Galois theory is sort of taking problems about solving equations and sort of translating them into problems about group theory. And in particular, sort of finite groups sort of play the main role there. And this is this is actually one of the real reasons we want to sort of spend time talking about the structure of finite groups, because after we've done that, like when we go to Galois theory, we'll be able to deduce sort of ramifications by sort of combining this reinterpretation of sort of solving algebraic equations in terms of field extension, and then in terms of group theory, we'll be able to combine that with our sort of knowledge of group theory to sort of deduce interesting things. So for example, like some of the original motivation for Galois theory was to understand like why there is no quintic equation. So why there's no sort of explicit formula in terms of sort of taking second roots or third roots or fourth roots or fifth roots and so on, that can solve a degree 5 equation. So, well, you all know the quadratic equation. There's a cubic equation, which is hard to write down. There's a quartic equation, which is really hard to write down, but sort of the same flavor, where you sort of just express the solutions to a sort of degree 4 polynomial in terms of like first, second, third, and fourth roots of the coefficients and sort of products thereof. But there's no, so one of the main results in one of the main applications of Galois theory is to show there's no such formula for degree 5 polynomials or sort of higher degree polynomials. And so that really sort of involves sort of all of the stuff. It involves sort of using the structure of finite groups that we'll have studied before, and then sort of applying it and sort of understanding how sort of, so the groups that are arising in Galois theory are some of the symmetries of the equations you're using. And so it's sort of understanding how the symmetries of the equations control the solutions and control how you are able to write those solutions, and then sort of using sort of some group theory to deduce actually like an interesting fact. There are other fun things you can do with Galois theory, and we'll probably get to some of them. So for example, thousands of years ago, sort of people were sitting around and they had time and sort of straight edges and compasses. They had time, ruler, and they had a way to sort of draw circles and a way to draw lines. And they asked themselves sort of what kind of shapes and what kind of angles you can construct sort of with just those tools. And so, for example, like, there's the question of like whether you can construct like a regular n-gon, sort of starting with just a straight edge and compass. And this is a question you can answer completely using Galois theory. The history, and maybe I think it was Gauss answered this more or less probably before Galois theory, but somebody can reinterpret things nicely in terms of Galois theory to understand what's going on. Okay, so that's the kind of thing we'll talk about in those 4 weeks. And then, weeks 13 through 15 is going to be the representation theory of finite groups. So in representation theory was a sort of generalization of character theory. So character theory is about sort of how a group can act by symmetries on a one-dimensional vector space. Representation theory is the study of how a group can act by symmetries on a n-dimensional vector space. I mean, if you didn't do finite groups, you'd also sort of be interested in like how you could act by symmetries on like a Hilbert space or like some other infinite dimensional vector space, but we won't get there. We won't get there in this class. And this is just a beautiful and very powerful subject. For example, the character theory already encodes sort of Fourier analysis on the real numbers and on finite abelian groups. This representation theory encodes some version of character theory. I mean, not just for all finite groups, but also for like sort of real Lie groups, if you know what those are. So like things like GLN over the real numbers. So it encodes sort of a version of Fourier theory for those groups. I mean, somehow it's very useful because of how groups come up in practice in mathematics. I mean, so like back in your undergraduate classes, like you might have learned about sort of, well, okay, I guess it sort of depends on whether you had a good teacher or a bad teacher for your undergraduate algebra classes. So if you had a good teacher, when they introduced the dihedral group, probably what they said is, this is, I don't have a color for digressions, but I probably should. So digression. And somehow all of today is digression, but anyway. So D2n is the dihedral group of order 2n. Okay, so it's a good teacher. So our world is branched. I mean, somehow unwittingly, your whole life has probably been branched along the same dichotomy. And mine too, not just yours. Okay, and so good teacher says this is the symmetries. So the rigid symmetries of so D8 should be of the n-gon, the regular n-gon. So by rigid, I just mean you're not allowed to sort of, so in the plane, rigid, I mean, you're not allowed to sort of distort distances in the plane. So sort of somehow this should be some, and these just look like rotations. So you can sort of do, if you have a square, so this will give you, this is a foregone, regular foregone. And so you get sort of 8, you get a group of 8 rigid symmetries. Well, one of those symmetries is just do nothing, just sort of send everything to itself. What's another symmetry? Yeah, so I could rotate around. I could rotate 90 degrees, 180 degrees. So I already said 0 degrees. That's just doing nothing. 180 degrees or 270 degrees. Sorry, you, like me, probably prefer radians. I don't know why I put these in degrees. So rotation. And then what's a symmetry that misses? That's only 4. I said there are 8. So what's another one? Yeah, great. So I can reflect about any axis. So I can reflect sort of the x-axis, the y-axis, or diagonal. So I can sort of reflect sort of along these like bisecting axes, or also along the diagonals. Okay, and it turns out, I mean, these are all the symmetries of a regular n-gon. And well, if you have sort of one rigid symmetry and you can sort of compose it with another one, you'll get a new one. And it's sort of fun to like think about how you can sort of compose 2 reflections to get a rotation, for example. And sort of any rotation can actually sort of be written down sort of as a composition of 2 reflections. Okay, but somehow this is a very concrete thing. So your bad teacher would have said this was the group generated by 2 elements, R and S, subject to the relations. So R is going to be something I'll call R and F. So that's bad. Okay, whatever. So R is for rotation, not reflection. And then F is for flexion or flipping. So R is sort of your 90-degree notation. So R to the 4 should be equal to 1. F squared is equal to 1. And probably FRF is equal to R inverse. So this is another way you could define the dihedral group on order 2n. I mean, it's not clear that there are only, it's not completely clear there are 8 elements in here if you sort of write it this way. So this is sort of these generators and relations notation, and we'll talk about this more, but probably you've seen this in some context or another. So they're saying you have 2 elements R and F, and sort of this group is sort of the smallest possible group, or sorry, it's the largest possible group where you sort of have sort of all products of R and F, but these sort of relations are forced to hold. Okay, and so from both these sort of definitions, it's actually like something to do to check that you get a group of order 2n. But I mean, over here, it's sort of something to do to even check that this group is not trivial. Like, you can sort of certainly write down things where you sort of write down some generators and you write down some relations. And it turns out sort of the only way those relations can be satisfied is if the group is just a trivial group. Whereas here, I mean, sort of, we immediately saw like, well, a reflection is sort of a non-trivial element. Okay. And so in fact, like the way you can sort of prove that sort of this presentation gives you something useful is by sort of showing that this presentation is sort of this rigid symmetry group. It's just sort of showing by that sort of has some realization. Okay, so this was a digression about sort of how you might have seen things in the past, but also about life, because in life, well, okay, in a mathematician's life, in mathematics, okay, at a certain point, if you're a mathematician, sort of, it's possible that life and mathematics become synonymous. I mean, not at all times, but at least like between 8 a.m. and 5 p.m. And so I guess for most of us, it's between 8 a.m. and 5 p.m. right now. So I'll go ahead and say life. So in life, you don't get groups like this. No one, like, I guess I would say if you're ever seeing a group like this, well, okay, not ever, but maybe if you ever are sort of working on something and you sort of run to a group and the way that group is given to you is by generators and relations, you should probably think long and hard to make sure you're actually working on something interesting, because odds are you aren't. There are some interesting things where like you might be handed organically this, but probably not. I mean, somehow this should, okay. So anyway, so in practice, you would never run into a group that was given to you sort of by a presentation and relations, even though like in somehow, if you're just trying to build things and write down examples, like this is sort of a tempting way to try and do it. I mean, you probably saw this in last term too, or sort of when you were studying rings, like if you studied a little bit of algebraic geometry. I mean, I don't think like every, like, even though, and somehow, yeah, oh, okay, that example won't be as good, so I'll just forget it. Never mind. Stick with this. Where, I mean, like this is how you run into groups. Like you run into groups by saying, here's this thing, like here's this structure. Like what are, like, so what's the structure here? Well, like you have a notion of distance, and then sort of you have this sort of geometric shape that you want to be preserved. And so then you're sort of looking at like, what are the automorphisms? So what are the maps that preserve this notion of distance and sort of this shape? Like that's what I meant by rigid symmetry. So you have some structure that you're interested in, like, because, like, I don't know, you can walk down the street and find a square. Like a square is something we're interested in. And certainly if you walk down the street, it preserves distances. So I somehow, like squares and distance preserving things are like things that actually matter. And then you might want to understand that thing better. And so you say, what are like these symmetries of this thing? And so this is like why group theory is useful, because this is sort of how it comes at you in like interesting problems, is that symmetries are somehow related to structure. So sort of inversely though, so the more structure equals fewer symmetries. So in this example, like, I mean, if I sort of ask like, what are, like, just for like, okay, square, like I can think of it just being, so I asked like for like a continuous map from the square to itself, there'd be sort of an enormous number of these if I didn't ask it to preserve distance. Because like I guess it's just like, I could sort of locally, like on a square, you could sort of just like locally distort the distance near one point and sort of locally just like spread things out like near one point and like do nothing everywhere else. And that would give you sort of a symmetry of the square that sort of preserved it like as a shape, but didn't sort of preserve distance on it. Whereas like, I mean, really you only get these 8 things if you sort of also require yourself to preserve distance. So the more structure you have, like, and then you ask like, what are the symmetries? So symmetries are like the automorphic, like, so a structure, I mean, sort of like some mathematical object, like a vector space or like a topological space or a manifold or whatever. And then sort of structure, I mean, sort of some like, you have some structure on the object. Like, so the vector space, like sort of, well, you always have the structure of a vector space. So maybe it's better to sort of start with like, okay, let me say it this way. So a set with structure, then symmetries equal automorphisms. So preserving structure. So sorry, better to be precise. So what's an example of a set with structure? Like a vector space is a set with structure. Like a vector space has an underlying set, but then it also has the structure where you can sort of add things, you can sort of multiply things by scalars, and so on. And so if you just look at sort of R squared as a vector space, sort of the automorphisms are sort of GL2 of R. So this is 2 by 2 invertible matrices. But like if I look at like R squared as a set, well, I just get sort of some, literally all maps from R to R, from R squared to R squared. So if I don't sort of remember this extra structure of a vector space, then I have many more symmetries. I can just take an arbitrary set map from R squared to R squared. Most set maps from R squared to R squared are not linear maps. And so this is basically the reason group theory is powerful and worth studying. It's because structure and sort of having additional structure is reflected in the automorphisms you see. And what we're interested in studying is always something with some structure, and sort of this idea that you can interpret that structure in terms of sort of giving you a smaller group of automorphisms just ends up being a very powerful idea. Like it's sort of what lets you say, it lets you deduce interesting things about the structure. So this is like, for example, really at the heart of Galois theory. So in Galois theory, this sort of manifests because, so you look at sort of some polynomial and you look at its set of roots, and sort of if you just think of that as a set, then like if you have n roots, then sort of the automorphism of the set is just a symmetric group on n elements. But now if you sort of remember these sort of roots of the polynomial, like you can think of it as being some extra structure. And sometimes that extra structure restricts the automorphisms in sort of an interesting way, and sometimes it doesn't. And that's sort of what Galois theory studies. So it studies like, for which polynomials do you get a smaller group of symmetries? You remember sort of the extra structure. These aren't just sort of n arbitrary things. They're like things that came from a polynomial. Okay. Right. So, okay, let's recap where we're at and then maybe take a 5-minute break. So where are we at? This is the class you're in. These are the things we're going to do. And here's basically how we're going to do it. Then I digressed. And I was sort of very philosophical for a while. And sort of I insulted some people. Not you guys, but maybe some of your teachers or sort of teachers I've known. Don't tell them. And then I was philosophical some more probably. Okay, that's probably a good place to take a break. So let's take a, why don't we take a break till, we'll round up, we'll take a break till 1:20. And then we'll just do sort of 25 more minutes and we'll say some things. Okay, so see you in 8 minutes. Okay, so what is a group? So a group, well, a group is a set equipped with some extra structure. What is that extra structure? So a group is a set G equipped with, well, you need multiplication and you need inverses. So multiplication is a map from the product of G of itself to G. So just sort of AB goes to A times B, takes two elements and sort of gives you something you call their product. And inverse from G to itself, such that if you have an element A in your set, we just, okay. We write this image under this inverse map as A inverse. So, and that's the data you need to give to sort of talk about a group. You need a rule that tells you how to multiply things. You need a rule that tells you sort of what the inverse of an element is. And oh, I guess you need an identity element. Well, I think there, yeah, so this is a fancy way. Okay, well, this is a really stupid way to say it. I mean, you can always write sort of the choice of an element of your group of a set as just being a map from sort of the set with one point. I only did that to be consistent with how I wrote multiplication and the inverse. And yeah, well, there are probably different ways you could choose which data to write down. But you need a rule that tells you how to multiply things. You need an identity element, and then probably it's at least useful to have an inverse of your inverse things sort of just written down as a structure instead of imposing it axiomatically. And these sort of satisfy some rules. So these should satisfy some compatibilities, which you can look up and I won't write down. But they are sort of associativity. The main ones exist and existence of inverses. So in here, existence of inverse is just now a rule about how multiplication. So this is saying that if I take A times A inverse, I get the identity element, or sort of the multiplication of A and A inverse. So the multiplication of A and sort of I of A is equal to E. Okay. I mean, somehow, well, okay, this is a stupid way to write things down, but I just wanted to sort of point out that it's just a set with some maps on it. And then, I mean, now a map of groups is just, okay, so I better put this definition in quotes. And again, there's no reason it would be helpful for me to write it any more precisely than that, so I won't. Okay, and then sort of, well, what's a map of groups? So it's just a map of sets respecting the extra structure. So sometimes we call this a homomorphism, but well, yeah, sorry. I don't actually know Latin or Greek or anything, so I won't. But I think this homomorphism, doesn't it literally mean same structure in some whatever language it is derived from? I think even if it's not true, like that's how you, like in mathematics, homomorphism means same structure. So it means sort of, it preserves the structure. So in here, this means like if F is your map, then like F of A times B should be F of A times F of B. So F of A inverse should be F of A inverse. F of E should be E. Well, there is a little bit of abuse to call sort of. But anyway, it doesn't matter. Right. And okay. These definitions are always true. Like a blank in math is a, basically, and at least sort of in sort of beginning graduate mathematics and sort of undergraduate mathematics, like this is always true. Like a thing is a set with some extra structure. Like a vector space is a set with sort of extra structure. A group is a set with extra structure. Or a ring is a set with extra structure. And a homomorphism is sort of just a map of the sets that preserves that structure. Okay, well, so that's the definition. So we have that now. What are some examples? Well, we saw some before. I don't know. Maybe you should tell me. So let's take 5 minutes and either on your own piece of paper or on the whiteboard, just write down as many examples as you can. Maybe 5 minutes is too long, like maybe 2 minutes. We'll do 2 minutes of just, so write down as many examples as you can. And you don't have to write down the multiplication table, so write down like whatever is enough to be recognizable to me as a group. Maybe as I see them appear on the whiteboard, I'll also copy them onto the notes. I might use sort of slightly different notation than you do. Maybe I'll stop here. I copied some examples that were on the board. Does anyone, maybe just throw out a few more interesting examples for people who weren't writing them on the board. Anything that I haven't written down already is fair game. You can just shout them out. Yes. So it's the fundamental group. Okay, what's another one? I should say it doesn't matter. If you don't know what some of these are, that's fine. It's okay. We'll either talk about them or we won't, and it doesn't really matter. Just ideas, have some examples. Okay. It's a good one. I feel you may have a geometric sort of topological orientation. Well, this is a good place to have that orientation. Okay, so good. And this is a good set. Oh, sorry, there's one I didn't get that was on the board. R cross for R any ring. Good. So this is equal units in R. Great. Yeah, so these are all good examples. So let's talk about a few of these quickly. So what's the symmetric group? Someone give me a definition of the symmetric group on n elements. Yeah. Great. So it's, yeah, good. So thank you. That was a very precise way to state it. And I appreciate that. I said a group is a set with some structure, and you said the set was all bijections from sort of a set with n elements to itself, and the group structure was given by composition. And so let me sort of write that the following way. So it's an automorphism, and then sort of as a set of the set 1, 2. This is a set of sort of the first n natural numbers, another way to write it. So automorphism, well, that just means bijection that preserves the extra structure. The extra structure here is, there is no extra structure. This is just a set. And so the automorphisms are just sort of all of the bijections. And that's what you said. Okay, great, thank you. So the symmetric group on n elements is just the automorphisms of the set 1, 2 through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on until you get to n. Great. And anytime, this is sort of inherent in the language, but maybe not in the notation, if you say automorphism group, it's a group. Because like the set of all automorphisms of any object, so here, unpacking object again, sort of for me, is a set with some extra structure. An automorphism is a bijection of the set that preserves the extra structure. So it's a map from the set to itself. It's sort of invertible that preserves the extra structure. And automorphisms are always a group because you can, the multiplication law is given by composition, and sort of bijections always have inverse. And sort of if the map preserves the structure, then the inverse also preserves the structure. So we can check this. Automorphisms of sort of some object of structure are always a source of groups. And in fact, it's the only source of groups, like both in like probably in a rigorous matter, but certainly in a practical matter. Like this was this point I was making earlier, is that all groups are automorphism groups, and like especially the ones you encounter, like these are automorphisms. So someone tell me how to realize GLN as, so GLN of the real numbers as an automorphism group. So this is n by n invertible matrices with real coefficients. So if n was 2, yes, in general, Rn. Yeah, thank you. Perfect. So this is automorphisms of Rn. And sort of what's the, with what structure? Yeah, okay, great. So yeah, so that's the groups, yeah, that's the group structure on the automorphism, is sort of matrix multiplication, which is just composition of these automorphisms. Like, so how are you thinking, like what are you thinking of as being the structure on Rn that's being preserved by these automorphisms? Yeah, exactly. So this is the automorphism of a real vector space. So Rn is a real vector space. And if I look at sort of all the automorphisms, so all the bijections of that set that respect this real vector space structure, I get sort of n by n invertible matrices. Let's look. So I won't write this down, like Z mod NZ, sort of you could realize it as sort of the orientation preserving rigid symmetries of an n-gon. So sort of that would eliminate the reflections in the dihedral group, and then you just get the rotations. What about, let's see, so someone wrote the unitary group. Let me do an easier one. Well, actually, sorry, yes, let me actually expand this example. Okay, well, before I do another example, let me just say GLN of R so this is n by n invertible matrices with entries in sort of any ring R, let's say commutative ring R. It's just the set of R modulo homomorphisms of the free R module of rank n. So this works sort of not just for vector spaces, which are just sort of free modules over fields, but it works sort of for free modules over any ring. In particular, sort of GL1 of R, which is just the units in R cross. Sorry. So it's just the units. So just the elements of your ring that have multiplicative inverses, sort of where the group law is just multiplication. This is just the automorphisms of R as an R module. So maybe, yeah, I'm gonna put R commutative here, just the hedge. And it's not. I don't really need R commutative here. I mean, there's a distinction between left modules and right modules if R is not commutative, and I don't want to get into that. And anyway, we'll basically never talk about it anyway. So maybe at the end of the class, we'll talk about this a little bit. Okay, good. So great. That's fun. Let me talk about the orthogonal group. So what is the orthogonal group? So rank n orthogonal group. Yeah, so that's one way to think it. Another way to think of it is it's just the group that preserves. So it's the automorphisms of Rn with, so sometimes I'll write, so with sort of the standard inner product. standard inner product on Rn, like this is sort of gives you a way to measure angles and sort of gives you a notion of distance in Rn. And if you look at automorphisms that preserve that, well, those are just really, and that's what I meant sort of by rigid automorphisms earlier, by sort of rigid motions earlier. So if I look at sort of automorphisms that preserve both the vector space, not only the vector space, but also sort of this extra structure of a sort of an inner product on your vector space, then what I get is called the orthogonal group. Okay, good. Here's a tricky one. So, and this one also applies for sort of any ring R, but let me just do the real numbers. So what's SLN of the real numbers? How can I realize that as an automorphism group? Okay, good. I said it was tricky, so you should feel nothing except that you confirmed its trickiness. That's good. Yeah, oh, sorry, was someone going to say something? That's a good idea, and you'll get something really close. You won't quite get SLN. You'll sort of, I think if you go where you're going to get sort of PSLN, which is a quotient of SLN by. But there's sort of a simpler way to do this, which is I can look at automorphisms of Rn equipped with the standard sort of multilinear form, alternating multilinear form on it. This is equal vector spaces sort of with sort of alternating linear form, alternating multilinear form. And so, and again, like how is the determinant? Well, it depends on, I probably think of people think of determinant lots of different ways. I mean, the determinant, at least for real vector spaces, like one way to think of it is sort of, it's the thing that measures how volume is scaled by its absolute value and like whether the orientation is changed by its sign. So another way you could sort of write this is sort of automorphisms that preserve volume and orientation. So this is equal to sort of R vector spaces with sort of volume plus orientation. But in another way, it's sort of just this sort of like if you look in like a basic linear algebra book when it's sort of giving the definition of determinant, well, and either it's going to sort of give this like really naive one in terms of permutations and sort of adding up the signs of all the rows. But if it's a little bit more sophisticated, then it's going to talk about multilinear forms and sort of there's a unique rank n multilinear form, and this is sort of a basis for the nth wedge power of Rn dual. Did you guys talk about this kind of thing last term? Okay. Good. So it's okay. It's sort of something like it's sort of, and like this example is like sort of no more foreign than sort of this thing. Like, and this inner product is a symmetric, like it's a symmetric form. Like this is an alternating linear form, but sort of asking it to be preserved is like you have some linear form that you're preserving. So that's the additional structure here. Okay, and so like the unitary group is sort of this similar. Like the unitary group, you have sort of this Hermitian inner product on a complex vector space that you're preserving, and so on. Let's see, what else did we have here. Okay, we covered most of these. Well, Michael, I'm going to pick on you because you gave this example. Can you give me a definition for the fundamental group in terms of automorphisms? Okay. Well, so I should say that depending where you look, the definition in terms of automorphisms might be the standard one. Okay, so let me sort of just say, I'll say this out loud. If you've never seen fundamental groups before, this is a concept from algebraic topology. It's incredibly important and intimately related to Galois theory, but we won't get into that. Maybe just remember that sentence for whenever you do learn about them if you haven't already. So a fundamental group serve, this X is a topological space, this biggest, and this little x is some point in topological space. You can look at sort of all paths in that topological space that sort of start and end at X, so all loops that start and end at X. And then you can sort of consider two loops to be equivalent if you can sort of deform one into another. So that's called homotopy. And so then sort of if you look at the set of all paths, and then you sort of look at the equivalence classes where sort of two things are equivalent if they're homotopic, so they can be deformed from one to another, well, that gives you some set, and you can equip it with a group structure where sort of the structure is just sort of you compose the loops. So you sort of do one loop and then you follow it with the next loop. And sort of turns out that gives you a group, and that's called the fundamental group of a space. And that's sort of the original definition of fundamental group. And again, sort of you can just ignore what I'm saying if you don't know any algebraic topology. And then well, another definition of the fundamental group is sort of in terms of covering spaces. So if there's something called the universal covering space for a sufficiently nice topological space, and it maps to X. So you have sort of, maybe I'll just write this here. So this is the universal covering space. So maybe I'll just write down an example of that. So if I look at the circle S1, well, this is just the complex numbers of absolute value 1. And this, the universal covering space is the real numbers. I send t to either 2 pi I times t. So this is, I'll call this map pi. So this is the universal covering space. And then sort of Z is equal to the automorphisms of R mapping to S1. So these are equal to sort of automorphisms of the topological space R sort of such that pi of automorphisms, I'll call them sigma, pi of sigma of t is equal to pi of t. Okay, and like if you think about this exponentiation and like Euler's identity and sort of e to 2 pi I is equal to 1, what you see is like this group, and this is just Z sort of acting by translation. So when I think of Z as an automorphism of real numbers here, I'm just saying it's the automorphism, like n is the automorphism that sends a real number t to t plus n. So this is a fun way to realize the integers is the automorphism of something. The integers are sort of the automorphism of sort of this universal covering space of the circle. So you can also say this is the fundamental group of the circle. We won't use that at all. I mean, this might come up again. It's a fun example to understand. It's worth understanding. And if you haven't taken algebraic topology or you're not sort of, but anyway, you're not going to be tested on this question, this example. Sorry, it's 2 minutes over. I'll stop here. I will stick around for a couple minutes if anyone has any questions.